But if I remember right, last time we did do like in the last 5 minutes, we reconstructed a polynomial, right? For this, so we practiced that again. So I erased it. I remember it had a bunch of root 2's in it. So let's see here. So the first term was probably just root 2, wasn't it? Root 2 over 2. Yeah. Okay. So P of x equaled root 2 over 2. And then the next one was probably plus, 5 root 2 over 2? So plus 5 root 2 over 2x, right? And then the next one was probably minus 125 root 2 over 2. Sorry? 25. There we go. Let's go back. 5 times 5 is 25. 25 root 2 over 2. X squared over 2 factorial. And then the last one was probably minus 125 root 2 over 2 x cubed over 3 factorial. Am I doing that accurately, quickly? Yeah? Okay. Okay. So then that's kind of where we were with last time. And then we get into B. B says, use Lagrange error bound to show that that thing right there is true. So I think it's kind of important for us to talk about what that thing is right there. So when you look at just that part right there, and somebody said, well, what's the meaning of that? What would you say? It's the error, yeah. Isn't this right here, isn't this the actual value of f of 1/10? So that's the true real value. And then p sub 3 of 1/10, that would be our approximation based on a third degree partial sum. So this is real answer, this is the approximation. So if you take the real answer minus the approximation, that should give you what the error is, right? Okay, so what the Lagrange error bound allows us to do is it allows us to essentially bound the error and say that the error cannot be any more than such and such, whatever we come up with. So we're going to bound the error, say that this is the highest the error could be. Another way to look at it would be to say this is the worst the approximation could be, or this is the most off that we could be, something along those lines. And so I think I will go with this. I'll go with their notation. I'll say absolute value of f of 1/10. Oh, it went away. Did someone, if it would somehow say, okay, so let's see here. So I'm going to say absolute value of f of 1/10 minus p sub 3 of 1/10 is less than or equal to, and I'm supposed to show eventually that this is less than 1/100th. So I'm going to use this Lagrange error bound to bound my error, and hopefully this will show me that it's less than 1/100th. So we're going to find out. So the Lagrange error bound kind of has 3 parts, I would say. And of the 3 parts, 2 of them are very formulaic, right? Essentially just plug, 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 and you're done. And the third part is you got to think a little bit. So the first 2 parts are, you reference back to the formula, the absolute value of x minus c to the n plus 1. So let's see here. X is going to be the number that we plugged in. C is going to be the centering point. So what's the centering point for this particular series? Nope. 0. So it says Taylor polynomial for f about x equals 0. So that's where we find all of our values. All of our coefficients come from x equals 0. So that's called our centering point. And then 1/10 is what was plugged in, right? So it's p sub 3 of 1/10 is supposedly approximating f of 1/10. So x minus c or c minus x, because we're doing the absolute value, it really doesn't matter. So I'm going to say 1/10 minus 0. And we're supposed to take that number to the n plus 1. So what is n? 3. It's going to correspond with that degreed polynomial that we used, and we used the third degree polynomial. And so 3 plus 1, of course, then is pretty easy from there. It's 4. And then that's over n plus 1 factorial. And since we just figured out what n plus 1 is, this will probably be the easiest part of the whole deal. All over 4 factorial. And now we've got to find that last piece. This part we have to think about it a little bit. This is going to be the max value of the n plus 1th derivative. So that n plus 1 that was in the top there, the n plus 1 that was down there in the bottom, factorialed, and the n plus 1 we're talking about now, it's all the same thing. So we're talking about the max value of the 4th derivative. Max value of the 4th derivative. So this is where we got to think a little bit. So let's go back up here and think about all the stuff we used to come up with this polynomial. So like this was f of 0, this was f prime of 0, this was f double prime of 0, this was f triple prime of 0. So if we're talking about 4th derivative, maybe we should figure out what that 4th derivative is, right? If we're going to try to figure out its max value, it'd be nice if we had some information about this. And because we've got that original function right there, I think figuring out the 4th derivative should be fairly doable. So I'm going to come back up here and just use this space to figure out what that 4th derivative is. So let's see here. This was sine, cosine, sine. So this is negative cosine. So it would be, what, 625 sine of 5x plus pi over 4. It's positive, and I guess it's not going to matter too much because we're just going to absolute value it anyways, but I think that's right, isn't it? Okay. Okay, so this is the 4th derivative, and so I would say, I said number 1, the calculator was allowed. I would say that a question like this one, I would say probably the calculator would not need to be allowed. Obviously it could be helpful, but I don't think it's necessary at all. So let's think for a second. We got a lot of stuff going on with this sine function. This is going to be the first time where it's kind of fuzzy, where, as a mathematician, we want to know this is the answer. And if you don't have this, you are wrong. And if you do have this, you are right. This is where it's going to be a little bit fuzzy, and we want to be like strategically reasonable on this. What do you think, Blake?
Wouldn't 625 be the max value?
I think 625 is the max value.
Sine can move up to 1.
So the amplitude, right? That's a really good observation. The amplitude is 625, right? Yeah. And you look at all this stuff over here. This is fairly complicated. I mean, technically this sine, I don't know, let's see if you guys can remember this from like pre-calc. What would be the period for this sine curve? No. Normally it's 2 pi, right?
5 pi over 2.
Other way around.
2 pi over 5.
2 pi over 5, yeah. So technically what you'd do is you'd factor that 5 out and divide by it to give you the new period. So technically 2 pi over 5, so it's really been squished by quite a bit by a factor of 5. And not only that, it's been shifted left, how far? Not quite. Got to factor the 5 out to see it. Pi over 20. So you don't really need to know all this stuff, to be honest. All you need to know is that this sine curve has been seriously modified, right? It's been squished down, it's been shifted left, and it's been stretched vertically big time, right? So Blake's observation of, man, we don't know like this 0 to 1/10 thing. You remember that z value is somewhere in between 0 and 1/10. So, if we had a graphing calculator, we could pin this down for sure. But because maybe on this one we didn't have a calculator that we could use, we got to look at this and say, man, I have no idea. I really can't say for sure what the max value is, other than it's for sure 625 or less. Do you see how you could based on the evidence that you have, you need to be able to say, I am for sure, I am super positive that the max value is 625. You might throw out there, hey, 310. And you might be right. I don't know. But if you don't have something to back it up, you don't have something to back it up. So I think 625 is really the only defendable value, unless you wanted to, plug in all the numbers between 0 and 1/10.
There's an infinite number.
And there's an infinite number of them. So for you to say this is definitely it, short having a calculator, you're going to fall short, right? It's never going to work. So with an amplitude of 625, does it make sense that I could say then that, the absolute or the max value of that 4th derivative is 625? I'm pretty for sure it's less than that, but that's very defendable, right? That's the highest it could possibly be. So here's what we're hoping. We're hoping that as we take this expression and we evaluate it a little bit, it'll fit within the error parameters that we've been appointed to work with, okay? So we do a little work here. Of course, 1/10 minus 0 is just 1/10. And 1/10 to the 4th is 1/10,000th, yep. So it's going to be 1/10. I might run out a little bit of room here. I hope I can fit this in here. I probably should have given myself more space. Let's see here. 4 factorial, of course, is 4 times 3 times 2 times 1, 24. I'm going to do a little bit of work here. Isn't 625 it's just 5 cubed, right? Or 5 to the 4th. So 5 to the 4th. So we can do some canceling, right? Because there's a bunch of 5s in 10,000, right? So maybe what we could do, let's see here. Couldn't we look at 5 to the 4th as really 5 squared times 5 squared? So if I canceled a 25 with 10,000, it's 10,000 divided by 25. $400, I think. Yeah. And then isn't there another 25 to cancel here? So it's 25 into 400. 16. That's kind of nice. So when I do that, I'm getting 1/16 over 24. So that's really 1/16 times 1/24, right? And this is going to easily fit, isn't it? So let's see here. 24 times 10 would be 240. And 24 times 6. Sorry? 120, 144, right?
Yeah.
So 240 plus 144, 384? Sorry?
I just did it long too, and I got some.
384? Okay. So this equals 1 over 384. And finally, in the end, we can say, yes, that is definitely less than 1/100th. So I'd say that if you don't have a calculator, I'm going to guess and say that probably the most challenging aspect might be the arithmetic with fractions and stuff that follows. It might take a little while. Sometimes they have this. You're going to see an example here in a second where maybe it's similar but less of a big deal. But this was right off an AP test, BC6. So this is definitely one where the calculator was not active. So they are expecting you to do a little bit of fraction work to conclusively prove that what you're supposed to be proving really is true. And if I remember correctly, this was a 2-point question if you're interested in point considerations. And the 2-point consideration was essentially if you had the right form with the Lagrange error bound, like if you knew how it all was supposed to kind of fit together and you put it together. And then the other point, I think, was just deemed analysis, aka arithmetic, leading to a number that truly was less than 1/100th. Okay? What do you think? Lagrange feeling a little less scary? Kind of, sort of, possibly? Okay. So again, I just want to emphasize to you guys, and I hope that you'll see my point. I feel like this part, plug, done. This part, plug, done. This part, you're going to have to do a little bit of reasoning. And then what follows is usually some form of arithmetic. Yes, ma'am?
What happens if there's like no maximum for that part?
There's got to be something, right? You should be able to quantify it in some way based on the tools that you have. So like that first one that we did that had involved e to the x, I would say definitely, the calculator probably is going to be active there because what was the interval? It was 0 to what on that one? Like, did we plug in 1/10 on that one too? 0.1. Okay, yeah. So to me, like the reason why I would say, hey, that one's calculator active is because do we really, is e to the 1/10, like is there any real tried and true pattern for determining like a value of e on an interval? I don't think so. But with like sines and cosines like this one, for sure, right? If you know the amplitude, you know it cannot be any higher than 625.
So on the E one, you just know that that's the highest it goes is at 1/10.
Well, I would say probably calculator would be active on that one.
So you just plug it in.
So I would just graph it and be like, hey, look on the right endpoint, that's where it's highest. And as to whether you want to use that exact value or not really depends on if the value you chose fits within the acceptable error. So, so like obviously e to the 0 is 1, e to the 0.1 is a little bit more than that, I guess, right? Because it increased. So maybe you would want to say, you know what? E to the first is 2.81828 or whatever, 2.78128. And so maybe you would say the max, like if you didn't have the calculator, you'd say the max value maybe would be 2. 2 would be a pretty defendable value. You'd be like, well, pretty sure it's less than 2. And hopefully that would be good enough to get you to your error bound, like to the max error that they've prescribed. So it really is tool dependent, right? If you got a calculator, it's kind of one thing. If you don't have a calculator, I've got to give you some way of navigating it that'll reasonably allow you to figure out that max value of that n+1 derivative. Okay. Anybody else? Questions for you? Our third one? Okay. So I think maybe what we should do here is give you all a chance to try this one on your own. So here we go. It says the 5th degree Taylor polynomial for g of x, and g of x apparently is some totally unknown function. It does not say anything. I just can't quite. I guess that'll just have to work. Doesn't say anything about g of x. It does tell us that the 5th degree polynomial is right there, p sub 5. It does give us a graph. It says the graph of g, and then what does that mean with the parentheses 6 thing? So we got a graph of the 6th derivative. So they don't really tell us anything about g, but they do tell us a little bit about the 6th derivative of g. Might be important. And then they ask us 2 questions. So question number 1, use the 5th degree polynomial that you've got right there for g of x to estimate g of 1. So let's use the polynomial. It's going to create a partial sum here, of course, just using those 4 terms. But let's estimate g of 1. And then B, explain why your estimate from A differs from g of 1 by less than 1/100th. Okay, so I'll just let you guys kind of explore and try this, and hopefully it goes well. I'll be around to answer questions, but we'll check this out. At A, taking the burden of adding a bunch of fractions off of you, I bet you A was pretty easy, right?
I didn't put any fractions in this.
Certainly, I mean, you're welcome to do it, but I mean, we'd say g of 1 is approximately equal to 1 plus 1/2 plus 1/72 plus 1/3600th, obviously aided by the fact that 1 to whatever power is just 1, right? So, you just leave it like that. I'm not too worried about you guys adding up the fractions. I know you could if you had to, but whatever. You okay? Okay, so then in B, explain why your estimate from A differs from the actual value of g of 1 by less than 1/100th. So, maybe we put that error bound in there and we say absolute value of g of 1 minus p sub 5 of 1. So this is kind of expressing our error. The actual value minus the value based on the partial sum approximation is less than or equal to, and these first 2 parts are the just plug it in kind of parts. So x minus c to the n+1 is what goes in the numerator. So what is x for this one? 1. And what was our c value? Right, that's our centering value. And this is all going to be raised to the n+1th. And so what's the n? Because if we know the n, we know the n+1, right?
5.
So n is 5, so n+1 is 6. And then that's over n+1 factorial. So again, like I've said before, I feel like this is the part where you can just go plug, 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 done. Right? So for you guys, not that complicated. The other part, a little more complicated, right? So you look back and you think, okay, I got to multiply this, whatever that is, times the max value of the n+1th, or in this case, the 6th derivative. And so I gave you no information about g, nothing about g prime or g double prime. I gave you like no information. But then maybe now is when you look, you're like, oh, I understand why you gave me that graph. It seemed a little odd at the time, but now I get it. There's this graph, and it's the graph of the 6th derivative, and that's exactly the thing that I need. So I'm supposed to figure out the max value of the n+1th derivative on the interval from 0 to 1, right? From my centering value out there to the number that I plugged in. So if you look at this, there are, to be honest, an infinite number of numbers you could plug in here, right? So if I decided, if I just said, hey guys, I have decided that, in my opinion, the max value of the sixth derivative is 500. Could I defend that number based on the graph?
No.
I'm pretty sure I could.
Easy.
Like, isn't the max value of the sixth derivative for sure less than 500?
Oh,
Oh.
that's what you mean by
500, like, I mean, this thing
that.
doesn't even really get up to 6, and I'm saying I think 500 would for sure be way higher. I mean, that's definitely higher than the sixth derivative's max value, right?
But you can go over the max value.
Sure, but think about what this would do. If I work these numbers out, do you think this would end up being less than 1/100th?
No.
I'm guessing not. Right? So I could figure this out and be like, hey, yeah, Lagrange error bound told me, well, I guess this would be 500 and for a numerator, 6 factorial, 720. So it'd be 500 over 720. Is that less than 1/100th? Nope. Now, based on the graph, I could say, yeah, 500. I'm guessing that my max value of my sixth derivative is something less than 500, but I didn't tighten it up enough, did I? Couldn't we do better? I mean, what if somebody's like, you know what, I think 500 obviously didn't work for our acceptable error bound, but I don't think you used a good enough number. What if somebody's like, hey, you know what, I think I could say for sure it's less than 10. Right? You look back at that graph and you're like, well, is that sixth derivative on the interval from 0 to 1 for sure less than 10? Yeah, it doesn't even get up to 6, does it? So to say that 10 would be an acceptable bound for that sixth derivative, sure. But again, I think if you tried this out, it would not fit within the acceptable error that we're kind of prescribed here, the 1/100th. Because if you did this, wouldn't you get 10 over 720? Which would be 1/72. Now that's a whole lot closer than my ridiculous idea of 500, right? But it's still bigger than 1/100th, and that's not okay. So you'd have to come back and be like, well, 10, is there any way, based on the evidence that I have, is there any way that I could use a number less than 10 to kind of express the max value of that sixth derivative? What would it be?
60.
I'd say 6. To me, 6 is probably the most defendable and at the same time useful. Like 500 is very defendable. 50, very defendable. 10, very defendable. None of them useful for our purposes, right? 6, I think is going to end up being quite useful, and it's also defendable. A really tempting number, I would say, would be 5, right? I mean, you might look here and say, I'm trying to draw this parallel over there. You might look and be like, 5, I don't know, doesn't this look like it's a little over 5? So what are you going to do with that? 5.7? 5.64? 38291? None of these are defendable, are they? You can't look at a graph and be like, yeah, absolutely, that is 5.86, and don't tell me otherwise. And you can't do that. But you could say, based on that, couldn't you say, well, 6 would probably be the max that I could confidently say would bound that sixth derivative? I think you could go with 6. And hopefully, if this all works out the way it's supposed to, 6 will work. So if we try this out, obviously the numerator is just 1. And couldn't you cancel 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Couldn't you just cancel this 6 off with that 6? Leaving you with 5, 4, 3, 2, 1, 120, right? And look, there we go. This is equal to 120th, which is less than 1/100th. So this is a pretty tight fit. I mean, you really kind of have to pick 6. 7 would barely work, wouldn't it? 7 over 720. Slightly less than 1/100th. But I think if you went with 8, that might be too big. Right, so you got what? Here would be the rule of thumb. In a situation like this, no matter what it is, whether it's the previous one or this one, you want to get as close as you can to a defendable value, right? Like if you just said, instead of 6, I used 5.9, I would really have to say do you really know? Like, are you for sure that 5.9 is higher than that peak? I just don't know that you can say that, but I do think going with an integer value of 6, right? You look at that across there, hey, that's definitely less. So 6 would be reasonable. I will never call on your powers of sight to be the differentiator between correct and incorrect, right? If you're like, oh man, my contacts, you know, unfortunately the rest of the students have much better eyesight than me, so I couldn't get it right. That will never be the thing that should split you between right and wrong. Should always, you know, they're always going to be designed so that as long as your eyesight, you can actually see the picture, you're good. It doesn't have to be super x-ray vision or whatever. Okay. So whenever that was, on Thursday, you saw the Lagrange error bound, and that was like the gas of like, do you feel any better about it?
It's pretty easy.
Right? So, or what I said, plug, 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 just get it over with, and then think a little bit. As long as you can do arithmetic from there, it should be in good shape. One thing I didn't mention, I was kind of wondering if you guys were going to bring this up. I think I'll bring it up now. Did you notice in part B it said absolutely nothing about the Lagrange error bound?
Yeah.
Why did I use it? Because isn't there another option potentially? What's the other option? In establishing an error bound. Say it again? Yeah, the alternating series error bound, right? Remember that? So the alternating series error bound says that if you've got a converging alternating series, then your error is bounded by what?
The next term.
The first neglected term. So this is where, this is a really nice example of where these two error bounds differ somewhat, right? So A, when you figured this out, that's not an alternating series. And so you cannot use the alternating series error bound, right? You can't. And then another thing to notice, sometimes people will be like, oh, I get it, the Lagrange error bound, that's just the same thing as the alternating series error bound. Sometimes it is and sometimes it isn't. In this case, it wasn't at all. Even if you did throw in some pluses and minuses in there, like if you turned it into an alternating series, did you notice that if you go according to this pattern up here, wouldn't the next term be something or other to the 7th over whatever? And notice down here for our Lagrange error bound, we did not use anything to the 7th. We used 6th degree information, right? And so whenever you've got a series that is jumping degrees, you know, like 1, 3, 5, 7, 2, 4, 6, 8 or whatever, the alternating series error bound, if it is that, it's going to follow the 2, 4, 6, 8 pattern, right? Because it's just the first neglected term, whatever that is. With the Lagrange error bound, it's simply going to be the n plus 1th term. And so if you're going 1, 3, 5, 7, it's just going to be plus 1, not plus 2. That makes sense? So if you had a series like this, I'll just write this off to the side here. If you had a series that was like, I don't know, let's say it was 1 minus x plus x squared minus x cubed plus dot, dot, dot. That's obviously it's an alternating function, right? So if you plug some number into that, then you could use the alternating series error bound, right? But you could use the Lagrange error bound as well, and they would seem to coincide in that instance. They'd seem to be very, very similar. In general, the Lagrange error bound should work on just about any series. The alternating series error bound only works on alternating series, right? Yes, I know, it's amazing. So you want to just pay close attention. Do I have an alternating series? Okay, well, I could use that. And to me, that's the easier one, right? Because all you got to do is like, what's the next term? Boom, done. Right? Lagrange's a little harder, but sometimes you just have to use it because it's not an alternating series. Good? Is that a okay comparison? You good? Okay, cool. Well, then let's move on. 9A. Okay. So I want to kind of set the stage for you a little bit what this is based on where we've been. So the very first day of this, we did the whole tricky graph with sine, and you guys figured out the errors, and McKenna was a good guesser, and Sean figured out the factorial thing. Remember that? So that first day we said, hey, what if we started using polynomial functions to approximate and represent transcendental functions, right? We did all that convergence, divergence, integral test, geometric series test. We did all those tests, and those are going to come back around here in 9.8. But in 9.7, we said, all right, do you remember those series, those polynomials we made back in the first day? Now we're going to start making these polynomials. So in 9.8, here's essentially what we're doing. 9.8 is saying, what if we took the stuff in 9.7 and instead of using the first 4 terms to do such and such, or the 5th degree polynomial to do whatever, what if we took those patterns within those polynomials, and what if we said, what if the number of terms went towards infinity? What happens then? Does that make sense? And so if we take those Taylor polynomials, Maclaurin polynomials, all those kinds of things, and we say, well, instead of using the first 4 terms, what if we thought about the terms just going on forever and ever and ever? That's what we call a power series. Make sense? So 9.8 is really just an extension of 9.7. What if we just kept the terms going? What might happen? So we did learn in the previous section how to make those Taylor polynomials. And, these are some key ones: e to the x, cosine of x, sine of x. I think we did a natural log one, and we did a few others. We're going to do a bunch more. So these potentially can be represented exactly, not just approximated, if the number of terms in the series is heading towards infinity, right? So we were, talking about how, like the Lagrange error bound, there's always going to be an error once you get off of the centering point. Well, what if we made the number of terms goes towards infinity? Now maybe it could be an exact representation instead of just like a really good approximation. So this hopefully will look really familiar to you guys. A power series centered at 0 is just going to be some number. The coefficients are just going to build as they go, and it's just going to be x to the 0, x to the 1, x to the 2, x to the 3, ... Looks a lot like what kind of a polynomial that we looked at in the previous section. If it's centered at 0, what did we call it? Sorry? The Scottish guy. Yeah, that's right. So this would be kind of like a Maclaurin because it's centered at 0. And then the other one, power series centered at something potentially other than 0. This is a more broad term, and it's what kind of a polynomial? Taylor polynomial, right? So these, I just want to point out that these are no different than what we've been doing. The representation here is maybe a little bit confusing because aren't we used to seeing a bunch of factorials and stuff show up? The a sub 1 covers the derivative value over the factorial. It's just like a general coefficient, right? So whatever the derivative was divided by something or other factorial, some derivative divided by probably the second derivative divided by something factorial, probably 2 factorial, third derivative divided by 3 factorial. It's just a very general way of putting it. That makes sense? But of course the idea is that we are having these go on forever and ever, and if they do, what does that mean? Like, what are the implications of that? Make sense? Okay. So a couple of general principles here before we get going. I think we'll open with this next time. We saw pretty, I think, conclusively, based on that first day. I don't know if conclusively might be too strong a word, but we saw, I think, maybe convincingly, that if you just keep adding more and more terms onto a polynomial, didn't we eventually fill the whole calculator screen with like coinciding graphs? Remember how they were basically just on top of each other? So, what if you made your window bigger? How would you get the graphs to coincide then? Wouldn't you just keep adding more and more terms? So I think you maybe saw that for certain graphs like, say, sine or cosine, maybe even e, I don't know if it was that convincing for you. But the idea here is that some of these are going to converge to for all real numbers. In other words, like if you want a better convergence, just add more terms, and we'll call it the radius or the interval of convergence will just keep growing and growing and growing. You're going to find that that's not always true. You're going to see one power series in particular, that no matter how many terms you add, the interval of convergence doesn't get any bigger. It doesn't like fill the whole calculator screen. It just doesn't. And then this makes the statement, in fact, most do not. So if you do have a power series centered at C, then one of the following is true. It's possible that the series will only converge at C. And when I say converge, I'm talking about converging to a value that is equivalent to whatever function it's trying to mimic. And also, number 3, there's a possibility like sine and cosine. These are examples of this. I'm on number 3, not number 2. Sine and cosine, stuff like that. It's possible that the series could converge absolutely for all x, right? In other words, if you make the number of terms head towards infinity, it's going to be a perfect representation of, say, sine or cosine, and that would be for all real numbers. But then there's this middle ground where, you know what? The power series does converge, but not just at c, but not for all real numbers either. We might find that there could be a radius of convergence that describes the kind of the area where the power series converges to the actual function. And I'm like really kind of calling on you guys to like think about those graphs that we've been doing, right? We did a lot of those graphs, try to get you to think about that. And like I said, we'll probably open with one when I see you guys tomorrow, where it doesn't really matter how many terms you add, the interval of convergence just doesn't seem to be getting any better at all. Okay, so what we're going to do with this is we're going to explore how to find this radius of convergence, and then by extension, how to find what we'll call the interval of convergence as well. But we'll start off with kind of a calculator activity tomorrow to kind of help connect and help bridge the gap between where you are now and hopefully where you'll be tomorrow at the end of class. Okay? Awesome. I hope our classes go by quickly for you. They go by quickly for me.